Okay, in this lesson I'm going to derive the capacitance for a spherical capacitor, and this is a different type of geometry. Capacitors can have many geometries. We've kind of looked at the parallel plate geometry in a lot of detail. So in this particular geometry you have two conductors which are concentric spheres. We're going to label the radiuses of those conductors radius A for the inside conductor and radius B for the outside conductor. So we're going to also imagine separating charges between those conductors. We'll put a positive charge on the inside conductor and a negative charge, equal and opposite, on the outside conductor. And so our goal is to find an expression for the capacitance. And what we're going to do is we're going to find the expression as a function of that outer radius. Okay, so we're going to let that outside conductor get as large as we want, and we'll see what happens to the capacitance as we do that. Okay, so just a quick reminder here: capacitance is the ratio of charge to the voltage difference, and in this case it's the voltage difference between spheres A and B. And so the mission that we have, first of all, is to evaluate the voltage difference between the spheres. So that would be defined as the voltage of A minus the voltage of B. So the way that we can do this is very easy. We know that a sphere of charge can be treated as a point charge. So we're going to substitute each of these voltages with the point charge formula. Using the respective radiuses. I should just put KQ there. So it's KQ over RA minus KQ over RB. And that would be the just subtracting the 2 point charge potentials. The KQ factors out. And that leaves us with that. And then if you look at this, if we try to get the common denominator of RA and RB, you take the product of RA times RB. So a little bit of algebra here. This becomes KQ right, so we're finding a common denominator, and that means that we have to multiply the first term by RB, and we have to multiply the second term by RA, and that gives us the numerator. Okay, so that's our voltage difference. So then we come on back, and this is VAB, and then our capacitance is going to be given by Q divided by the voltage there. And you'll notice the Q shows up here and in the voltage term, so the Q's will cancel out, and we'll be left with 1 over K times the product of RA, RB over the difference RB minus RA. So the things flip in that term because you're dividing by voltage. Okay, and that's the answer. That's the expression that we want. We have our capacitance. If you graph this, let's sketch it out, what that might look like. So we're going to graph capacitance on the vertical axis here, and our variable is going to be the radius of the outer sphere. Okay, so the variable here is going to be RB. And then RA is going to be something which is fixed. So we'll label that. And of course, RB is always going to be greater than RA because of the setup here that we have. If you were to actually graph this function out, it looks something like this. You will have an asymptote where at RA, okay, that will be an asymptote. And you'll also have another asymptote which shows up right here. And the capacitance will basically be a function which is kind of hyperbolic. It's gonna approach an asymptote in both the vertical direction and in the horizontal direction. And hopefully this makes sense to you, because the capacitance, if you think about the vertical asymptote, if you think about the radius of A, you can imagine that as RB gets closer to RA, the gap between the two spheres is becoming really small, and so the capacitance should increase when you make the gap between the conductors very small. That's very much like what is the case for parallel plates. Okay, so that would explain why the capacitance basically approaches infinity as you approach RA from the left, or I'm sorry, from the right. So that would explain that. There's another asymptote that shows up here, and the value of this one is going to be actually given by the radius of A divided by K, and it's pretty easy to show that is a limit. If you take the limit of the capacitance function that we just came up with as RB approaches infinity. Okay. So if you were to come on over to this function here, if you were to let RB approach infinity, what would happen is that RA essentially would become 0, or not important. These two terms would just become 1, and up on top you'd be left with RA divided by K. So that's what gives you the asymptote here. So the capacitance does not approach 0 as you make the radius of B become infinitely large. Instead, the capacitance approaches this other limit, which comes straight from this. I would encourage you, if you want to look at the mathematics of this, I would encourage you to graph this in Desmos. And to keep it nice and simple, what you could graph is just try to graph a function that looks like the one that we just derived. So you don't have to graph everything like this, but graph y is equal to 5x divided by x minus 5. And if you do that, it's kind of like y is equal to capacitance, x is equal to the radius b, and 5 is equal to the radius of a. And I think it's kind of good if you can see, for yourself what a function like that would look like, and in fact that it has asymptotes there. So I'd really highly encourage you to graph this function, y is equal to 5x divided by x minus 5. Graph that in Desmos and see that you in fact get something like this. The other thing you'll discover if you graph this in Desmos is that you will see that there is another part of this graph where you have negative capacitance, or you have a capacitance for a negative radius. Of course, those don't have any physical meaning, and that's why we're not really considering them in our discussion here. So what you really care about is when you have a positive capacitance for values of RB that are greater than RA. Okay. But otherwise, I hope this kind of seems reasonable to you. The main idea is that you have capacitance between two conductors when they're set up like this, and as you make the gap between them small, the capacitance will grow. So that is the key idea. Okay? All right, well, have fun.